Okay.
So what is a radiance field anyways, is the title of this talk. The overall goal is to give you guys an idea of radiance fields in general, and then break that down to NeRFs specifically. So goals of the presentation. First of all, I hope to wow you with the concept of what a radiance field really is, talk a little bit about the physics, and also describe the progress that's been made in this area overall, as well as how it's applied to robotics, and then also to provide technical details specific to neural radiance fields and what that means, particularly with their architecture and training procedure. So what is radiance? Radiance. So for any point in 3D space, radiance can be defined as the amount of light energy or light intensity that is passing through that particular point in one particular direction. So it's energy through this one point in one direction. And what is a field? So fields. In mathematics, fields are often defined as what you would call like the field of real numbers or the field of complex numbers. So just the set of all complex or real numbers. That's not what we're talking about for fields in this case. You could think of it more as like a temperature field or something where you have some function that's mapping or assigning values to something. And in the case of radiance, we're just talking about mapping or assigning a radiance value to each point in 3D space, where this mapping is also a view-dependent value. It's a view-dependent scalar radiance value. So it's some scalar number that's dependent on the direction that the light is passing through that point. Okay, so what is then a radiance field? So we have the ideas now, let's try to put them together. We now have a radiance field being a representation of something in 3D space where for every single point, we know the amount of light energy passing through that point from every single possible direction. So every single possible point in continuous space for every single possible direction. Okay, very simple. Simple to wrap your head around, right? Okay, how do we actually go about making something like this? We need some intuition, we need some examples of what this actually means. And I have a little video to share, if I can get my mouse over there, of some radiance fields that were created by software that some people over at NVIDIA developed. So here's what they might look like. You see these weird clouds, what are those? You really have a photorealistic and view-dependent representation of some scene in 3D, which it's really amazing that we're able to create things like that. And what I want to show in this figure in the top left, you see that dependent on the viewing angle that you have, so these are the same points, different shapes, you have different color that you're actually going to see. So physically, depending on where your camera is or where you're viewing this scene from, you're going to see different things because that's how things are in real life, right? You have view dependence. And then we're winners. So let's go on from here. Okay, but how is the question I would ask next. How do we go about making some representation like this that seems impossible, I would at least think. So it's all about optimization. You take a bunch of different view-dependent, different images from different views. So for example, the room that we're sitting in right now, if we took a bunch of images from different perspectives and we optimize some model of the scene, that's generally how this process works. I'm saying this very generally because there's different meanings for what that model can be, and we're going to talk about that more on the next slide in different approaches that people take to actually making radiance fields. But it's all about this view dependency, because in space, if we have a camera and we know where it is, and in space we have another camera and we know where it is, and we have a bunch of them, then we have an understanding of what this space should look like from a bunch of different places. It should make a little bit of intuitive sense that we should be able to then make or optimize some kind of representation based off this data, but we just need a way to do it. So that's what we're going to do. Take data and we optimize some model. Now let's look at the models. So there are two different, I would say, frameworks for approaching this. One is an implicit model and one is an explicit model. So I'm going to start with explicit actually, because I think that generally makes more sense to us. So this is encoding your scene representation, so our 3D scene. into discrete 3D points. So this is more the idea of for some set of points in your 3D space. Let's say we have 10,000 points. We could have 100 points. It doesn't matter. It'll matter for how good it looks, but some amount of points in a set. And for each of those points, you could come up with some kind of optimization algorithm where we're trying to find the optimal set of some parameters to represent the scene. And those parameters could be things like the color from one particular view. And now you just have to develop an algorithm that can optimize the values for all those points. So that's why it's explicit, because we have to actually hold these in memory somewhere. They have to exist. Now, with implicit, this is the idea that came up with neural radiance fields. You're encoding your scene representation into the neural network, which literally means you're training the neural network, and its weights end up representing your scene. This works because, and this is continuous because for a input as a point, as a 3D point, as an input, you're able to get your view-dependent color and your density for that point. So if, in theory, you could sample infinitely many points, then you could have a continuous representation of the scene, is how that works. Because the network ends up being your representation of the scene. That's the idea. That's what I'm trying to show here. This is the general way people show neural networks. So we have a photorealistic and view-dependent 3D continuous representation of the scene, which I think is really cool. Now what are some papers where this has been taken in different directions? How have people done this in the implicit way? How have people done this in the explicit way? So in the implicit way, I think this area of research actually started with scene representation networks, SRNs. Back in 2019, this paper, I don't think gets a lot of hype, but they were the first ones to take camera poses for particular images. So pose camera images. Pose just means your position and orientation of your camera in space, and be able to come up with a 3D representation of the scene. And as you can see in the arrow pointing to the figure there, it looks meh, right? They look kind of basic, maybe like 2010, 2012 video game graphics, not so great. But I think where things really took off was with the neural radiance fields paper back in 2021. So they came up with different tricks, different methods to be able to actually express the really high frequency details of things like this microphone you see. What I'm zooming in on there is the grill of the microphone. It's actually able to capture that detail, which that hadn't really been done before, and then that drew a lot of interest to this field. And then there were suddenly thousands of papers that exploded onto Google Scholar. And then from there, and in the implicit side, we've then had a lot of interest from NVIDIA, because you really need a lot of GPU power to do these. So they are interested in that area of research because it's something that people are going to buy their GPUs to use. So they came out with this paper, Instant Neural Graphics Primitives, Instant NGP, where this took NeRF from, with this paper taking sometimes 1 to 2 days to train, to now a couple seconds. Giant leap forward. And they did that by coming up with, it's essentially a data structures approach. They took a different approach to how we are storing and encoding and accessing the scene information. So they completely Frankenstein took apart the simple idea of just having a neural network that encodes the scene, and then they added a bunch of stuff that makes it a lot faster. And then from there, ZipNeRF isn't necessarily an improvement, it's more of a different avenue. They went to try to improve upon the original structure of the neural radiance field paper and made that much, much faster, to the order of not as fast as an instant NGP, but still to the order of just a couple seconds to train. Now on the explicit side, here's where we can talk about different ways that you can actually model that scene that you're optimizing, rather than a neural network. So with planoxels, in the top right, that was the idea of using a voxel grid. So this is actually written by the same authors that wrote the neural radiance field paper, which were some folks over at University of Berkeley. And they said, okay, do we actually need to have the neural network? What if we just try to optimize a voxel grid? So voxels is a volumetric pixel. So think like 3D cubes. Voxels is what Minecraft is. So if you have something to connect with. And that worked really well. It's also really, really fast. but also it's going to take up a lot of memory, right? Because this is explicit, we have to store it in memory. The benefit of implicit is neural networks are only going to be so big, and you have a continuous representation of the scene, which is useful, right? You can put it in your pocket or put it in your small computer, your robot, and take it with you. And we're interested in things that we can put on robots and use to do robotics applications. Next, another really big paper in the explicit side is 3D Gaussian splatting. This paper basically made NeRF much more, or this idea of radiance fields much more real time as well. So this is even faster than instant NGP, I believe. But this was more of an approach that you have a bunch of individual points where you're able to optimize values of radiance for each of the points. And actually that figure of the man standing like this, that was from that paper explicitly. So really fast rendering. Rendering is the generation of a 2D image of your 3D model from some view. So that's a big area of research within this. How can we render things really fast? So it's very important in computer graphics and for video games and for things like that, and for virtual reality. Now, the last paper I want to talk about here, I know this has been a long slide, is K-planes. So I just think this is a really interesting one in the explicit side because they essentially came up with a generalization for explicit radiance fields where you could have a 2D version, 3D version, 4D version, 4D being video. So you could encode a radiance field into like a moving video, so you could have a radiance field of something that's dynamic, which is just, it's a very interesting concept I'd like to learn more about actually. So now, robotics. So how can we use radiance fields in robotics? I'm glad you asked. So we'll start with the top left, just talk about some different cool applications of it. Maybe you're not familiar with them, expose you to the ideas. First is path planning. So you can actually use a radiance field as your map representation. So if you train a model, let's say we're talking about a neural radiance field, so we have a machine learning model, a deep learning model, particularly a neural network, that we train with a bunch of images of the space we're in, and we can get that points in the space. From all those points that we generate, we can create a mesh. That's what you're seeing here. And then within that space, you could plan a trajectory for a robot to move through the space from some start position, some start goal, to a final position, avoiding collisions using different path planning algorithms. So that's an open area of research that's very interesting, especially since these could potentially be trained on board robots and then they could use them to navigate their environments. So pretty cool there with just a camera, right? SLAM on the top right. SLAM is the simultaneous localization and mapping problem. It's often referred to as a chicken or the egg problem. Which comes first, the localization or the mapping? It's the idea that your robot is somewhere in space, or rather on the Earth. It could be in space if you wanted to. Space as in R3, the real R3 space. And you want to figure out where you are while also creating a representation of your environment that you were within. So to figure out where you are, you need a map of your environment. But to create a map of your environment, you also need to know where you are relative to things around you. So that's kind of why it's a chicken or the egg problem. And the common approach to doing both of those things is to switch back and forth between them and use updates to your localization to improve your map. So people can do that with NeRF as well. What you're seeing is a real-time approach to using, or semi-real-time. I believe this is built with instant NGP as the NeRF model, but they were doing SLAM where they're continuing to build a representation of the environment and rendering views of it from their robot. I think that's really cool. The last thing I wanted to talk about in relation to robotics is active 3D reconstruction. So this is part of the next best view planning problem in BV, where you have some agent in space. It could be a drone, it could be an underwater robot, and you want to choose what location it should move to next in order to increase. In general, the next best view problem is I want to do something better with a minimal amount of distance, so where should I go next? And particularly that could be 3D reconstruction. Like in this example, maybe we start off here. I want to determine where the best place to go to make a 3D reconstruction of this building is. So you have some approach to determine where that is, and then you could make a radiance field reconstruction with just a camera of whatever scene that you're in, as long as you can figure out the pose of that camera in space, which that's also another problem. But lots of cool stuff that you can do with radiance fields. Now, specifically, let's talk about the neural radiance field and get more of an idea of what that means and how is that distinct from radiance fields in general. So for the neural radiance field, let's talk about inputs and outputs. Input-wise, we have x, y, z. That's a point in R3 in the space of real numbers. That's just some 3D position. And we have theta and phi. So that's viewing angle. So for our camera, what's this? What's this? Let's figure out what we're looking at. And from those, it's able to determine our G and B channels of, so that's our red, green, and blue channels, it's our color of something, and we have the density. The important thing to note here is that for that point, you're gonna it doesn't matter what the theta and phi are, we're always gonna get the same density, right? Because remember what we talked about with radiance fields. The color is what's view dependent. So the color is the only thing that's going to change when we're changing our theta and phi. And we don't exactly give it a theta and phi directly, that's kind of a lie. We'll talk about more of that a little bit later on. Now let's talk a little bit about the architecture. So it's actually, as far as neural networks go these days, it's pretty simple and minimal. It's just 8 fully connected layers with a width of 256. That means there's 256 different inputs to that layer. Fully connected, meaning that all the neurons, all those 256 neurons, are connected to each individual neuron of the next layer. So all 256 of one layer connect to every single of the 256 on the next. So, that's why there's so many different connections in neural networks, because, yeah, that's a lot of connections. And they all have a ReLU activation function in between. So that's like flat for things that are at 0 and then linear, and then it gets flat again. So activation functions, if you aren't familiar, are just functions that the output from each of your layers of your neural network go into that allow neural networks to model linear or nonlinear behavior. Because otherwise, each of the layers are essentially just linear functions. If you just have a ton of linear functions. But if you put it through some activation function, then you're able to start modeling nonlinear behavior. That's the idea of having those in the first place. And at the end, we have a sigmoid activation function. So that's just a function that's S-shaped. It's often used to make things more of a probability because it maps it between 0 and 1. A fake probability, really. Now, I'm sure y'all are curious about what this means. What is this function that we're applying to our input? Our input x, where that bold x is our XYZ position. Now, if you also notice down at the end, we have in green that same function being applied to D. So that's our viewing direction. Viewing direction is how we're handling our theta and phi that we were talking about. So that's just a direction vector, a normalized direction vector. And then our reds are our outputs. So if you see that right 2 layers before the end, we're outputting our densities, our sigma, and at the very end, we're outputting our RGB. So there's some weirdness to this architecture, but let's talk about that function. So that function is the positional encoding function, which if you've heard of transformers, you might be familiar with. Transformers, the machine learning technique, not the movies. That's from the paper that I think was written back in 2019, Attention is All You Need, where they proposed the transformer architecture. And one of the things that they used at the input, such if you're familiar with transformers at all, the idea is that you have some, I think they call it a token, which is like a vector that represents a string of text, and they're able to use something called the attention mechanism to have context between, like, oh, I can relate this part of the sentence to this part. So that's what they use this potential encoding function for, but they use it for something else here. So let's talk a little bit about how that is working and what this math means. So essentially what they're doing is for the x, y, and z of our position, so for each of the directions of position on our input, we take it, that's what P is. P is saying that's our x, y, and z. So for each of them, let's just say for x, we're going to do this for every single piece of that. So for x, we do 2 to the 0 times sine of 2 to the 0 times pi, then cosine of 2 to the 0 p times x, and so on and so forth to some dimension L. That's something they just played around with until they found a good value for that. And what this is doing is it's taking, so what you're seeing is for each x, y, and z, we're essentially stretching it out in a way, right? So we had our just initial x is just some scalar value, could have been like 0.3, and now we've taken the sine and cosine of it to different powers, basically. So what this actually is a Fourier basis that you're taking. So it's an expansion, or you could think of it as, like in linear algebra terms, it's known as a Fourier basis, like the Fourier series. So you're decomposing some output into some combination of sines and cosines, because essentially the idea is that combinations of sines and cosines can represent any signal. So that's what you're trying to do with this. And the idea by expanding it out is that you can represent higher frequency details. Because remember earlier on, I talked about how NeRF came up with some way to represent the high frequency of something like the grill of the microphone, right? Or it could represent hairs on your head a lot better. So this is the key contribution they came up with that was able to do this. They repackaged that idea of positional encoding and said, hey, what if we do it? And they did it to each of their x, y, and z on the input, and they did it to a random spot in the middle, and then they said, hey, let's do it for the direction vector as well, and then immediately get out the density, and this worked phenomenally. So now let's talk about training. So we have an idea about the architecture, we know what's going into it and what's coming out of it, but how do you actually train something like this? Because I think the core ideas of NeRF are found in the training. So for that, we need to talk about volume rendering. For volume rendering, the idea is that for your camera position, you cast a ray, which is just a line, that goes from your origin of camera in 3D and into your space where this can represent our scene. This is the scene that we're trying to model. It's our soon-to-be 3D model of the scene. And you'll essentially have a ray for every single pixel in your grid. So you could think of volume rendering as essentially integrating values along this ray continuously to get some value for what that pixel is going to be. So that's the idea of rendering, and that's what in computer graphics they do when you're playing a video game, and that's like what rendering speed is. How fast are we able to get this 2D image of whatever scene was modeled for the game? Now I want to talk a little bit about the physics ideas that are attached to this and how this corresponds to the radiance field. So in physics with light, we have absorption, we have outscattering, we have emission, and we have inscattering. And this is all relative to when that light energy or intensity is going through that point in space. That's what this is showing, like we were talking about before for radiance, right? So some of it is absorbed, some of it is scattered, some of it is emitted, and some of it is brought back in. So you have light coming in, light going out. Now we need to have a way for our volume rendering equation to model this so that we can actually capture the ideas of radiance within this equation. And it doesn't do it perfectly, but we're able to do a little bit of this. So this is the volume rendering equation. Just to break it down a little bit, this big C at the end that we're trying to get, this is the color of that pixel. And this bold R that you see a couple places in here, this is the equation for the ray. And that T that you see is just your position continuously along the ray. So what's our T along R? That's all we're asking here. This O is just the origin of the ray, and D is just your direction vector. So we have some direction from some origin, and we have some point that we are along that direction, right? Because we're just scaling the normalized direction vector. That's all the ray is. Nothing too crazy. And like I was saying before, we're doing some kind of integral from T near to T far, Tn to Tf. So from the beginning to the end of the ray, we integrate along it, and we're getting some color for that ray. Now what are these terms that we're looking at here? Let's try to break those down a little bit. So the first is the accumulated transmittance. So this is modeling the absorption that occurs. So this is essentially the idea that as we go further away and further along this ray, more light is going to get absorbed. And so there's going to be less contribution further along it. So things that are closer up, the light is going to have more of an effect on what the color is going to be. And in this context, you can basically think of light as a combination of brightness and color. How bright is this color that we're getting here? And absorption is also modeled a little bit in our density equation. So this is just saying, what is our density sigma for our ray at a point T along the ray? So we go over to our ray, we go to a point T, and we want to know what the density is. And remember, that's something the NeRF gives us. So we could say, okay, what's our density here? That's the more dense you are, the more light you're going to absorb. So that's going to be connected and coupled with that accumulated transmittance term. Now we also model emission. So that's color. Think of color as light that's emitted from something. And this is how we're handling our color along the ray at some point T for a particular viewing direction. And hey, what do we have here? We have a ray, we have some particular viewing direction, we're going to have some color here. If we had a different ray coming through here and hitting that same point, we're going to have a different color that we're going to render. So that's kind of how that's all modeled within this equation here. Now, we don't actually get to model outscattering and inscattering with this, and if we did, I imagine we would have an even better representation, but no one's figured out a way to do that yet. There are ways in physics. I think there's approaches you could take using fundamental equations of physics to come up with something like this, but I don't think you'd be able to do it fast at all. And the original approach took 1 to 2 days to train the model, so I don't know how long it would take from a very, very fundamental modeling approach. Now, okay, now we talked about that. How are we actually training this? And what I'm showing with this picture here is for our ray, we get some estimate of color, right? So for our ray, we got some estimate of the pixel color. That's what that is. And for each ray, we had a bunch of images we trained on, right? So we know what the pixel color is supposed to be. So all we do is find the error between those two. And we do that for a ton of different pixels. And we do that a ton of times, right? That's what we do in optimization. So we're finding the mean squared error of this. So we're literally taking the mean and we're squaring it. That's all there is to this. We take a bunch of different pixels. You could even think of it as doing a bunch at the same time, right? We could have a vector of estimated pixel colors and a vector of the ground truth and find the difference between that. And then that is our loss. In machine learning, when you have a loss, you can pass it back into your model using back propagation, and you can update all your weights. And you just keep doing that and doing that and doing that, and eventually we have a beautiful model that comes out. Now, there's one last thing that I want to talk about with this, because I think it can trip you up. Because, well, we're training this to be able to get the right color, right? We're training it to guess the right color. So it would seem like this is going to get good at being able to estimate what our scene should look like from different views, right? So it should be good at estimating images. But what does that have to do with the 3D model, right? So, weird. Well, what went into determining this color? What other terms do we have in here? That's interesting. We had a density term, right? We had the density of a point that's not view dependent. So essentially in this training approach where we are forcing the model to get better at estimating what the pixel color should be, it also has to get better at predicting what the density should be. So if it doesn't figure out the density, it's not going to figure out the pixel color. So then we're getting densities of points. And there's one other point that I wanted to make. So, okay, this is maybe starting to make more sense, but I think there's still a little confusion on the training. So how are we getting this? How are we getting this? How do we get How do we get this value, and how do we get this value? Because there's no equation for those. So how do you get them? Well, we have a model that we're training, right? And what are its inputs? Points. And what are the outputs? Color and density. So we just use our model to get the density and the color, and that's how we're able to get these along the ray. So we can use the model and say, okay, if I had this ray for this pixel, what would the density and color be here, 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 all along it, and then those are the values we need for the rendering equation, and then we're able to render the color. And then we get our loss, and then it continues and continues to improve itself. And then you have a great model. Now, there's one more thing I wanted to mention. So how is it doing this continuously if we're sampling points along this ray to do it? Because that sounds very discrete to me, right? And if you wanted this to be a real integral, then there sure as heck must be continuous points along here that we're dealing with. So yes, this actually isn't continuous. They, in the paper, use a discretized version of this equation. So sadly, we have to replace the integral with a sum. And we're summing points along the line. So it's not actually this equation, but it's very similar. And they actually came up with a neat way to make it seem more continuous, which this also helps with encoding the high frequency information in scenes. And to do that, they did something called stratified sampling. So this is an approach that they came up with. I'd say it's a trick that they came up with. So what they did is they take this ray and they break it up into in bins. So equal size bins, so just little lengths along it. Each say they could all be length 0.1 or something. And in each of those bins, they randomly sample a point. So instead of uniformly sampling points along here, they're randomly sampling from each of the bins, and this allows the model to handle more continuous behavior because it's a better approximation of something continuous, or at least in practice it worked. So just mean squared error. This is the loss. That's how you train it. That's a radiance field, and this is it. Hope you enjoyed.